Today we're looking at some sample problems from section 10.2 on using the fundamental counting principle. And I'm going to begin with exercise number 8 on page 541. This is the 12th edition that I'm working from. So it could be in some cases that you're working from a different edition. Okay, 6 factorial. Our directions here say that we're to evaluate each expression without using a calculator. So 6 factorial, 6 times 5 times 4 times 3 times 2 times 1. That's the definition of the factorial. So let's see, I'm going to multiply pairs. That's going to be 30 times 12 times 2. 30 times 2 is 60 times 12. Okay, so over here, get a 0, 12, it looks like 720 possibilities. So we're not using a calculator. Number 12, we have 6 factorial over 6 minus 3 factorial. Okay, if you remember algebra, anything in parentheses should be simplified first. So we're going to simplify 6 minus 3 to a 3. And so that's 6 times 5 times 4 times, and this is my little trick to save me some writing. 3 times 2 times 1 is actually 3 factorial. So I can cross those out. So I have 30 times 4, which is 120. Okay, and let's do 14 as well. We have 10 factorial. We're given 10 factorial over 4 factorial. 10 minus 4 factorial in the denominator. So again, I'm going to simplify what's in the parentheses first. That's going to give me a 6 factorial. So 10 times 9 times 8 times 7 times 6 factorial. So I'm matching it with the larger of these two in the denominator, and then we'll have 4 times 3 times 2 times 1. So the factorials cross out. 4 times 2 is 8, so we can eliminate that. 3 goes into 6 too. So now we're left with 10 times 9 is 90. Times 7 times 2 is 14, so 90 times 14, 36, and we're ending up with 1260. That looks awfully large. Let me look at this again and make sure I haven't made any errors. 4 times 2 was 8, so we got rid of that. 3 went into 6. I can't count the 6, that's what's wrong. Okay, let me erase that. Alright, I have already canceled the 6 factorial. So when I have a 3 left over, I have to put it into 9. So it's going to be 3 times 7 is 21 times 10 is 210. That looks better. I knew the number looked awfully large. Okay. Now let's take a look at number 18. It's 14 factorial. This time we're told we can use the calculator. So I'm going to use my TI-84. If I can get it to work. Let me go to my SmartView calculator so you can see that. Okay, it takes it a moment to load. So what we have to remember is how to find that factorial button. So again, we're on number 18, which is 14 factorial, so I want to enter 14. And then I want to go to Math, Probability, number 4 is factorial, and then I'm going to enter. Okay, so we're getting 8.7178 times 10 to the 10th. Okay, let me jot all those numbers down. 8.71782912 times 10 to the 10th. And it turns out that our book puts this in standard decimal notation. So 782912 times 10 to the 10th. So to enter that, if we had directions on my math lab that said we couldn't use scientific notation, we need to move our decimal point 10 places to the right. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 8 here, and then we have to add 2 zeros for the other 2. Get my commas in the right place. So we have 87,178,291,200. That's a rather large number. Okay, one more with the calculator. Let's do number 22, and I think I'm going to have to move that to the next page. We have 19 factorial over 9 factorial times 10 factorial. Okay, so this is a little bit tricky to do on the calculator, and that's one of the reasons I selected this one. So let's go back to our TI-84, and I want to clear. Okay, so I'm starting with 19, and I want to go to math, probability, I want number 4. And I want to divide that by, and I want to put parentheses around this so that everything is considered in the denominator. So I'm going to do a 9 factorial, number 4, times a 10 factorial. So I need 10. I'm going to go to probability, and number 4 is factorial, and then I want to close the parentheses. So I'm saying this whole thing is in the denominator. If you don't include the parentheses here, what will happen is it'll take 19 factorial, divide it by 9 factorial, and then multiply that answer by 10 factorial, which is equivalent to saying that both the 10 factorial and the 19 factorial are in the numerator. Okay, now I'm going to press enter, and I'm getting 92,378. So very important to remember on the calculator to put parens around that denominator to make sure both of those stay there. Okay, now we move to some problems, and first of all we have a problem on arrangements of n objects when some of them look alike. And there is a formula for this. What we do when we have objects that look alike is we take n factorial, which is the total number of objects, and then any of the parts that are repeated, we take those factorials in the denominator until we have taken care of all of the ones that are repeated. So let's look at an example in number 26. In 26 we have heebie-jeebies. Okay, so what we want to do is count the number of letters we have. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13. So now we want to count the ones that are duplicated. We can see we have 2, 3, 4, 5, 6 E's. we have 2 B's and we have 2 I's. So this is coming from the E's, this is coming from 2 B's, and this is coming from the 2 I's. So now what we need on our calculator, and again remember that we want to include parentheses around the denominator. Okay, so let's go to our calculator. Okay, I'm going to clear it. So I'm going to do 13 factorial divided by, and I'm going to put parentheses around the denominator. I want 6 factorial times 2 factorial. Notice 2 factorial is 2 times 1, so that's actually 2. So I'm going to take kind of a shortcut here. 2 factorial again is just 2. And then press enter. Alright, I'm getting 2,162,160. Okay, so that's what we use in the event we have some items repeated. Okay, let's go to number 32. How many 5-digit numbers are there in our system of counting numbers? So we have the digits 0 through 9, which are 10. There are 10 of those. But what we have to remember in this case is that the leading digit cannot be a 0. Otherwise, it wouldn't be a 5-digit number. So we only have 9 choices for the first one. We assume in this case repetitions are allowed if they don't say anything about it. They want all of the numbers, so repetitions would be allowed. So each of the following ones could have 10 possibilities. So we get 9 times 10 to the 4th. And that would give us 9 with 4 zeros. So 90,000 possibilities. Alright, 36. Schedule. We have in this case Alan, Bill, Kathy, David, and Evelyn, and how many ways could they do each of the schedule one member to work in the office on each of 5 different days, assuming members may work more than one day. So we have 5 days, and you'll notice with a fundamental counting principle, a lot of times I'll think, okay, I've got 5 days. How many choices do I have for the first day? They're assuming people can work more than one day, so repetitions are allowed. So that would be 5 raised to the 5th power, and that's 3,125. Okay, and 38. We have select 2 members, one to open their next meeting and another to close it, given that Bill will not be present. So since we have one to open and one to close, Bill's not present, so there are only 4 choices. Someone different to do the closing would mean 3, so we get 12 possibilities. Okay, let's stop at that point, and I'll continue with the sample problems in another recording.